Today we continue discussion of devices and systems used in communication systems. The first one we want to discuss is VCO, voltage controlled oscillator. Last time we discussed the oscillator. You know we have an LC oscillator, and the frequency, oscillating frequency, is determined by the structure. And VCO is an oscillator, so there is a frequency, but the frequency can be controlled by externally applied voltage. So the frequency of the VCO is a function of time. First one, it has a natural frequency, Fn. That means if the external voltage equal to 0 or there's no externally applied voltage, then it's just like, for example, LC oscillator. So this is called natural frequency, oscillating frequency. Or sometimes it's called free running frequency. Then it will add an additional term. This term is related to the voltage from outside, and with some constant coefficient here, Ko. So this is the output frequency of VCO. And for this VCO, we have input, which is the voltage of here. And we have an output, which is the oscillating frequency. But we will consider the change of the oscillating frequency as the output. That means it's not the total, it's only this part.
So MT is the
MT is the externally applied voltage to the oscillator. Keep in mind, this one is not the input, because for oscillator we don't need to have any input. And this one is not the power, not the 12 volt or 5 volt, not that power. It's just externally applied voltage to a terminal that can control the oscillating frequency. Remember, when we discuss the oscillator, the 12 volt source or 5 volt source does not change the oscillating frequency. And the oscillating frequency only depends on the L or the C or some other, but not the power.
So which one did you say was the also called the free running frequency?
This one.
Okay.
Means if this one equals 0, then that's frequency equals this one. It's called free run. So we define transfer function. Transfer function means, as we all know, it is the output divided by the input. So the transfer function is here is the Ko, and which is the change of the frequency then divided by the external frequency amplitude. So this is called the transfer function. We can see the unit of the transfer function is here is hertz, here is volt. So this is something. The unit is hertz per volt. So that is the first one. The second one is phase comparator. Phase comparator. Or sometimes we call phase detector.
What's that function called?
So voltage controlled oscillator. A phase comparator is used to compare two phases. So that is from this name. And phase comparator is a nonlinear device. It is nonlinear device. Actually, it is just a multiplier. That means the output equals the product of two input. The output spectrum the output frequency consists of the sum and the difference of the two input. Consists of a sum and difference of the input. From trigonometry, we mentioned in the first chapter, the product of two cosine functions equals remember cosine alpha times cosine beta. What we have? We have a half cosine alpha plus beta plus half cosine minus beta. If we consider alpha as omega 1 times t, beta equals omega 2 times t, then we see here we have 2. This is the frequency add up together. This is the frequency subtract from each other. So the output frequency, so this is the multiplier together, and the output frequency, we have the sum and the difference of the two input frequencies. So we know the theory on this. And the transfer function again, the output divided by the input is KD, this detector, and equal to VD divided by delta E. Delta E is the error in the phase, means the phase difference. And this one is the output voltage. If we have two different phases, delta E is not equal to 0, then we are going to have output voltage. So the output voltage divided by the input phase difference, this gives us the transfer function. Oh, what is the output? The output VD equals KD times delta E. Same thing here. Transfer function K0 equals delta F times delta V. Right? Then delta F will be equals this one times this. And if we draw the picture, it's not exactly like this. Later time we are going to discuss in detail. Actually, this one is approximate, so we can put our approximation here. Approximation. So this is the delta E, and this one here is the E or the VD. Actually, it will be a sine function like this. So we can see if delta E is smaller, for example, like this, in this part, this sine function can be approximated with a linear function. That is VD equals KD times delta E. So the slope here, the slope is K times D. But after some value, if the delta E is large enough, then this one will not be linear. So if we want this to work, we need to make sure this delta E cannot be large enough, must be small enough. Later time again, we are going to combine everything together to discuss more in math to see how this works. All right, next one is the famous phase lock loop. Or for short, PLL. You're going to see this PLL lots of times. A phase locked loop has three basic components. Three components. The first one is the VCO, just discussed. The next one is the phase detector. And then there's a low pass filter. It's called a loop filter or loop filter. So we discussed all these three already, and we just draw the diagram for the fixed lock loop. And we have this. What is this? Which one of these three is this? Multiplier, right? That means this is phase detector, right? We mentioned phase detector is nonlinear device. Actually, it is just multiplier. So this one is phase detector, right? Multiplier, we have an input. So this one is A times sine omega CT plus theta I. That is the input. Another input is from here, and we just leave this here temporarily. And the output is here, so this is the output. Output is xt. We know this output equals this one times this. And then here we have a loop filter. And this one is just a low pass filter. And the transfer function, the system function is Hs. And here we get the output of the loop filter. We write as E output sub 0, sub O. And from here we are going to have VCO. And the output of VCO is 2 here. Because VCO is oscillator. It has a oscillating frequency. Suppose this one is B times cosine omega CT plus beta out. This is omega C. Omega C, this is omega C. Both are omega C. You may ask, if this one omega C, how about if they are different? Okay, if they're different, you make them the same, then the other part, the difference will be considered as here. The difference omega times T will be combined with this term, but we still call this term as theta out. How this works? Now, these two we can see multiply together. From the trigonometry identity, we know we have two terms of this. The first one is the add. This one will give us on 2 omega C, the sum. The sum will be 2 omega CT plus theta 0 plus theta I. And there's difference. It will be this one minus this. This one minus this. These two cancel. And we have only this one left. So theta I minus theta O here. Then, so we have this term and this term at the output of the phase detector. Then we have a loop filter. Loop filter is a low pass filter. Then this term will be gone. So this one will be gone, and we have only this left. So that means if we have phase difference at the input, then we are going to have some output here. And this one will control, used as the externally applied voltage to control the oscillating of this VCO. Then that means this frequency, oscillating frequency will change. If this one changes, that means hopefully it will make this one closer to the frequency here. Then make this difference smaller, so this one will be smaller. So after several loops, we can see the frequency will be the same. So this is how PLL works. Any questions on this? At the beginning, these two may not necessarily the same. If they are not the same, that means this one is large. If this is large, then this is large, this is large. So the external voltage is large. That means from here, if this voltage is large here, then multiply by this gain or the transfer function, this change of frequency will be large. So the change of frequency, large change of frequency will bring this one closer to this. So make this difference smaller. Okay, so next cycle, it will be smaller, then the change will be smaller than after several, it's very fast, after several cycles. And this phase will be very close to this, then the frequency will be the same. So phase locked loop will keep the frequency identical, but the phase is still a little bit different. because that give us the error. The error between the phases will give us the voltage to control the VCO. Right? How this works, the math we already mentioned here. We erase just the Einstein function. Let me maybe I can write here. So for example, A times sin omega c t theta I times times B, and B will can combine here cosine omega c t plus theta 0 here. This one will be equal to half AB and sin theta I minus theta 0 and plus sin 2 omega c plus theta I minus theta 0, and we have these two terms here. And after the low pass filter, we have only these two left. With this term left, theta I minus theta 0, because this has high frequency. So this is how theoretically how this works. Once the frequency are identical, or the phase, there's only a little phase difference. This is called the loop is locked. The phase lock loop. Suppose the natural frequency is here, Fn, free running frequency. At the very beginning, we may have, if the input frequency is this much different than this, smaller or large. In this part, within this range, we can make this loop locked. So this is called capture range. As we said, remember here, right? We only work at this part. If your phase difference is too large here, it won't be locked. So that means there's a range here. And this one is the capture range. We have a natural frequency here. If your input frequency here is within this range, away from the natural frequency, we can guarantee it will be locked. So that is called capture range. Once it capture, means it is locked. Right? Now, locked means this frequency and this frequency are identical. Then, by some reason, this input frequency can be changed again. Okay? Now, this gives us a larger range. This one to here. Here. Once it is locked to this, then it can deviate from this, give us a larger range, but we can still make it locked. So this is called pull-in range. This is called hold range, hold-in. This capture range is also called pull-in range. So also called this. And this is called hold-in range. Any question on that? So we make I have a simple example to show you the difference. For example, I want to catch you. Right? The first time I want to catch you, you need to be, for example, like 5 meters away from me, within this range. So this one is range here. Once I catch you by some like numeric connection, now once I catch you, we hold hand or something. Then you can go further away, but this range can be larger, for example, 8 meters, but I still can catch you back. So this is holding range. Right? But the first time you cannot be this large. And now we show you an example about the calculation based on phase lock loop. No, it's not VCO, that is how to calculate questions about the phase lock loop. Suppose the VCO assume the natural frequency for the VCO equals 200K. And the external frequency, the input frequency, equals 210. Okay. So you see there's difference. And the transfer function, KD, transfer functions, KD equals 0.2 volt per reading. The transfer function for the phase detector. And the KF is 1. That is the low, the gain for the low pass filter. And just the filter, so the gain equals 1, we assume. And for that, there's an amplifier, and this one can be combined together. But the gain for the amplifier equals 5. And K0, which is the gain or the transfer function for the VCO, equals 20 kHz per volt. That means for each volt of external voltage, the change of the frequency will be equals 20K.
So what is KD representing?
KD is the transfer function for the phase detector for the for this guy.
Yeah.
Okay? So we put here. This one is we put the gain here. This one, the gain equals KD. This gain here has two parts. The first one is the K, is called KF, and then it's KA, it's combined together. Eh? And this one is KO. We may use this one. See this clear. Okay. This one frequency here equals the natural frequency equals 200, and the external frequency, input frequency equals 210. We have some definitions. I suppose we define after this here, but we define this in this example. So the first one is the open loop PLL open loop gain. The open loop gain is the multiplication of all the gains around the loop. That's easy, right? Okay. So we write KL equals it is equals KD times KF times KA times KO. All the gains multiplied together. So we are given all these numbers in this thing. The 0.2, 1, 5, 20. So this one times 1, okay, so equals 20. Okay. Now we need to see the unit. Unitless. Radians and 20 kHz and V cancel. So that will be 20 kHz per reading. And this one, we can represent this one in radians per second. By definition, this one will be equals, we call this kV. In this one is equivalent to this, but it's called kV. And this one, by definition, equals 2 pi times KL. So this one multiplied together, it will be 40K, 40 pi times So that's 20K, so it's 40K times pi. And the radians per second. Radians per
Is that
second.
KC?
Where? Here?
Yes.
KL. L is here. KL. Right? And we rewrite this one in unit of radians per second. We ignore the derivation for all this, but this is the formula we need to use. We just this number multiplied by 2 pi. This is open loop again, and in radians per second, you just multiply by 2 pi, and equals 20K times 2 pi is equal to 4 pi. And we can convert this one into dB, and this one dB equals 102 dB. What we do is you multiply this K, this pi equals 3.14, then you take the log base 10, then times 20, because we are talking about the voltage. Right? So times 20, that's give us 102 dB. Right? So that is the first one. Do we know this KD equals 0.2? And this one equals 1, this one equals 5, this one equals 20K hertz per V. This one equals volt per radians. The next one. What's the frequency change we need to make this loop locked? That's easy, right? The natural frequency equals 20. The input equals 200. That is 210. So that is will be. So the change of frequency is Fi, the input frequency, minus Fi minus F natural. So equals 210 minus 200, so equals 10K hertz. So we need to make the change of 10K hertz to make this loop locked. If we want this one to be locked, that means the phase difference will be like 10K. What is the output voltage of this VCO supposed to be to make this 10 change? Because this 10K change is because of the error here, or the output here, right? This one, it's here. We want this one to change 10K. We want this one to change 10K. Then we want to know what is the voltage here we need to make this change of 10K. So now you can see the gain equals 20K, means for each volt it will change 20K. What we need is only 10K change. So this one will be equals 0.5, right? Right. This will be so the first one, PLL output voltage will be V out will be equals to delta F over K0 equals 10 over 20, so equals 0.5 volt. Alright, so we know this one here need to be 0.5 volt. This one 0.5, that means this one 0.5. So what is the output here supposed to be? Because the gain equals 1 and 5 add up, multiply together equals 5. So this one here, definitely, this one will be equals 0.5. Alright, so the next one is the output voltage phase detector. That is the phase detector, right? Phase detector output will be equal to, that one is VD will be equals V out divided by Kf times Ka, so equals 0.1. We go backward from here. This is the requirement. Then we know the output here must be 0.5. This gain equals 5, this gain equals 1. That means the voltage here, or the output of this phase detector must be equals 0.1. 0.5 divided by 5. If the output of this phase detector equals 0.1, then what is the phase difference? What's the input to here? That means the phase difference, the delta theta E, theta E, right? The error of the phase. What is this one? Now we see the gain. Right? This is 5. It's called static phase error will be equals theta E equals this is the output, and the formula, okay, we erase the end of the first one, right? So that is the output Vd divided by the transfer function for phase detector. And this one will be equals 0.1 over Kd is given as 0.2. So that one will be equals 0.5 radians. 0.5 radians, okay? We make this one as in degrees, so it's a better look, it's 28.65 degrees. So what does that mean? Remember, if we draw this picture here, like this, this one must be like 28.6, it will be here. And this one looks like 90 degrees here. Right? It's the same function. And 28 degrees is about 1/3 here, so that's 20. This one is. This is, at this point is 29 degrees. Right, the last one, holding a range. Because we want to make this capture just 10K, then what is the holding in range? Holding in range, we imagine from here. It is larger than this one, right? Right. The definition for the calculation formula for holding in range is delta F max equals plus or minus both sides and half pi times KL. That's the definition. That's the formula. So that is KL, we already calculated, equals 20 K per radians, and this one times 2, right? So that's one plus minus 10 pi, 10 K pi, right? So that's one plus minus 31.4 kHz. So once this one loop is locked, the external frequency can deviate within this range. This one will still be locked. Right, so we have several formulas to memorize this. Here, this is definition we already mentioned, and this also here, and this here, and this, and all this. Definition, formulas, plug into numbers, we can calculate.
Is that so your delta F max?
This one, yes.
Yeah. So
the maximum frequency that you can hold
I'm
in.
saying, is that a plus? That's a plus and minus.
Plus
10,
minus
10 over right there. What is that?
this one.
Yeah. What is that?
10K.
Okay.
K times pi, because you look at this one. This is 20K.
Is that K over
K pi.
K over 5?
No, not just K times pi. I write pi here. Forget the K here. So K pi.
Okay.
Okay, any questions on this? Good? Alright. What you need to do is understand all these concept definitions and the given formulas. And, most importantly, understand how this works. Right? So sometimes in other textbook, they may give you different names. For example, this one, they may be different names, but you do not just remember these formulas. You need to know what this means. This one is easy, right? The output frequency equals the input voltage multiplied by the transfer function or the gain of this. And all these are actually, they have the same meaning, right? Just several definitions. This one, the holding range is plus minus half pi times the open loop gain. The open loop gain is the multiplication for all the gains around the loop. Okay, we finished the discussion for devices. Next one, we are going to discuss several systems in communication, in analog communication. Frequency synthesizers. If we are given a few fixed frequencies, for example, give you a 10K, 1 or 2 or 7, for example, just give you 10K. How can you generate other frequencies? How can you give me 5K? Oh, easy, you divide by 2, right? How can you give me 20K? Okay, you multiply, it's harmonic. So this generates new frequencies from 1 or several fixed frequencies is called frequency synthesizer. Any device or systems that can do this is called synthesizer. We are going to discuss several frequency synthesizers. The first one is called multiple crystal. Then the second one is a single crystal. And the next one is PLL, I just mentioned. And pre-scale. And IC, integrated circuit. And we have some others, integrated circuit, the radio tuning frequency synthesizer, but we are going to discuss the first 3 in more details. First one, multiple crystal. That means we have a model, for example, like this. First one, this is a crystal, and suppose this frequency equals 100K. And we have another one, 110K, and we have another 120K. I need to list all of them: 130K, 140K, 150K, and 160K, 170K, 180K, 190K. I put all this box here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crystals here. Their corresponding output frequencies are 100K all the way to 190K. And I have another set of crystals. Their frequencies are 700K, 710. No, not 710. 800K, 900K, 1 meg, 1.1 meg, 1.2 meg, 1.3 meg, 1.4 meg, 1.5 meg, and the last one is 1.6 meg. Right, we have 20 crystal oscillators. Their frequencies are fixed. What we do here is we have a bus here. This bus is just like in the computer. If you take any computer courses bus, you just take any one here. Right? So I put at this point, pick one, and I have another bus here that can choose any one of these frequencies. It is here, and these two, there's some other oscillator module or something, that is just the auxiliary circuit, like a buffer. That's not important. Important thing is this will multiply together, called a phase detector multiplier. So mixer. In this case, we call this one as mixer. They refer to the same thing, but with different names and different situations. Here we call this mixer. Just two multiply together. Okay. Now this one, this input controls any from here. This input controls any from here. Suppose the first one chooses this one, the second one chooses this one, and this one is multiplier. That means the output here will be the phase, will be the difference and the sum of the frequencies. Which one, sum or difference? Okay, depends on the filter. So you have filter, you choose the sum or the difference. So suppose we use this two. What's the lowest frequency we can have? The difference, right? Okay, this one minus this, so it equals 600K. So if we choose this and this, we can have 6K here. Any question? Or if we use the sum, then we can have 800K. So now we have a filter here. So I said band pass filter. Right? Then either we choose 600 or we choose 800, so we get this. Now I have a question to ask you. What is the lowest frequency can be generated at this point? Keep in mind, you choose any one from here, and you choose any one from here, then you subtract or you plus. What is the minimum frequency that can be generated from here?
Can we use two at the top? Two at the tops?
Two? No, you can. This is the box. You can only choose one from here,
Okay.
and you only choose one from here to this.
Yeah, 100K, right?
You need to choose two, then subtract and minus.
No, I mean 600K. 100K. So.
I know the minimum will be the subtraction, right? Subtract, so I will, if I choose this one here, I will choose this one here, then this one 700 minus 190, so that's going to be 510. So this one here will be 510K. Do you think this is the minimum frequency that can be generated from here?
Yeah.
Right? Because if you use this one 600, you use this one will be 590, 580. So the minimum is there, right? And if you use this one, it will be larger, right? Okay, so that is the minimum frequency. Can we have a 510? Yes, this one with that. Can we have 520? Yes, this one with this one, right? Can we have 530? Yes, this one with this one. So this one with this will be 600. Do we have 610 from anyone else? Yes. This one minus this give us 610. This one and this give us 620, and all the way to here give us 700. How about this one? This one minus this give us 710, then all the way to 800. Then what is the maximum frequency can be generated here?
1.6 million plus 190.
This one plus this one, right? Because we want to use the addition here, so this one. So the maximum will be equals to 1790 kilohertz. Alright, so this is the range of the output range of this multi-crystal frequency synthesizer with a step 10K. Okay, this one can be used for AM transmitter or receive. Actually, this frequency band is between the AM. Amplitude modulation. If you listen to your radio in your car, what frequency listen? Anyone still remember any frequencies? 950?
Not AM.
950, right? Okay, 950 is within this. The next one will be 960. There's no such thing as 965 because the bandwidth, if each one is 10. Right? 950, 960, 970, all the way the highest is can be this one. If you go more than this one, it's beyond the AM range. The minimum actually is 535, but the lowest can be from 540 start. But this one gives us more than enough. This one is used for AM modulation and demodulation. Any question on this? Alright, so that's good, right? This is called multiple crystal. Alright, next one we discuss only first three, right, in detail. The next one we generate more frequencies with a single crystal. For example, the single is called master 2, called master oscillator. That frequency we have here, and this one equals 100K. So we have this 100K and this one. I want to use a network called divided by 10. It's called divided by n network, but the n here equals 10. Now this output will be equals 10K, and we have a 10K in this way also. Then followed by another one divided by 10K, divided by 10, and so this one will give us 1K, and we have 1K here. Then we do the same thing. Next, divided by 10, then divided by 10. This one will be equals to 100 hertz, 100, and this one. And then we have another one here, divided by 10. So this one will be equals to 1 hertz. And this one will be 10 hertz. This one will be. And this one equals 10 hertz. Is this clear? We start from this single crystal, and we use divided by 10 network. Divided by 10, we get 100. We start from 100K, and we get 10K. We get 1K, 110, 1 hertz. So we use 6 divided by 10 network. 1, 2, 3, 4, 5. 5. Okay. Next, here we are going to use the multipliers, but we call it harmonic generator. That means generate multiple of the input frequencies. For example, if you give me 1 hertz, I can get 2 hertz, 3 hertz, 4 hertz, and so on. It's called harmonic. And here we have a harmonic. Harmonic is called harmonic Generator. Generator 1, the first harmonic. So this one will give us a frequency from 0 to 900K. And the step is 100K. Because the input equals 100K, so we got 0, 100K, 200K, 300K, all the way to 900K. And the step equals 100K. Then this one, same thing here. Generator 2. What do we have here? That is 2, harmonic generator. Same thing, all this. We are going to have from 0 all the way to 90K. Because the input equals 10K. And the step equals 10K. So 0, 10K, 20K, 30K, all the way to 90K. Then that's easy, right? Harmonic generator, the third one, harmonic generator, fourth one, harmonic generator, fifth, harmonic generator, sixth, and this one will be from 0 to 9 Hertz. This one will be from 0 to 90. This one from 0 to 900. And this one from 0 to 9K. Right? Like this. And the corresponding steps are just the input frequency. These two add up together. It's a mixer. Right? Again, multiply. Multiply means the input signal multiplied. Thing times the cosine or thing times the harmonic signals multiplied together. That means the frequency just add or subtract. And these two, we do the same thing, multiply. And these two, we do the same thing, multiply. And then with these two, multiply. And then we do this to multiply. Okay, this is the final output. Keep in mind, this multiplier, mixer, again we call it mixer here, give us the sum or the difference of the input frequencies. Okay, now tell me what is the largest frequency we can generate here? $900 here, right? Alright, we add to this 990, then we add to this 9K, 900, so the maximum is 999,999. What's the minimum? Oh, the minimum is all zeros. So the frequency can be from 0 to, so basically from 1 to 1 meg minus 1. So the minimum is, the maximum is less than 1 meg, and minimum equals just 0, or you can see 1. We use a single crystal as the master oscillator, and we use a divided by n network, and we also use a harmonic generator. This one multiply, and we use some mixer, then we finally get all the frequencies. The step size depends on the smallest frequency here. And in this case, we have 1K then here. If you do not use this one, then the smallest will be 10K. Alright, the next one we discuss phase lock loop. Frequency synthesizer. First one we draw the PLL. PLL is this here. That is a phase comparator. Then we have an amplifier. And then we have VCO here. Amplifier always called a loop filter. And we have VCO here. And this one will be our output here. This one is the reference frequency. And this one usually use, for example, use a very crystal. It's a very stable frequency. For frequency, for example, equals 1 meg. The reference frequency equals 1 meg. It's generated from a crystal oscillator. It's very stable, and that determines the quality of the system. Right? So this looks like if we connect this one directly to here, that is PLL, right? But we add another thing here, and this here is called divide by n. For example, n equals 10 here, network. Divide by n network, and example here is n equals 10, and then we go this into here. How this works? Right? Ignore this first. We connect this one directly to here. Once this is locked, this frequency will be equal to 1 m, right? Two frequencies must be identical. That's called locked. But now, this one here, this FO is divided by 10. So we can say that once this is locked, this frequency will be equal to this 1 meg. And what this frequency is? This frequency equals F0 here divided by 10. So F0. So once this is locked, it's locked, F0 divided by 10 will be equal to 1 meg. That means F0 will be equals to 10 times 1 meg, so equals 10 meg. In general, F0 will be equals to n frequency, right? This is the reference frequency. This is the network n. So n can be anything. This reference frequency can be anything. Okay, that's it. See? You choose your reference frequency, you choose your factor n, you generate multiple frequencies. For example, you can by any method control this n and change this n, then you change this frequency. And the advantage of this one is very stable. We know once this is locked, this one is always correct. Right? So this frequency, the quality depends on the reference. And we use the best, okay, the crystal oscillator. So it's very stable. Then this frequency is very stable. Any question on this? All right, we finished the frequency synthesizers. Next, we discuss